think about formation of the carbocation, then that part is exactly the same for SN1 and U1 mechanism. Then the carbocation can be attacked by a nucleophile, which then gives you the SN1 product. On the other hand, in the absence of any nucleophile, which is good enough to attack, then it can undergo an elimination, and the water or whatever else is present in the solvent, that can act as a base under those circumstances. And so we'll often see a competition between SN1 and U1 mechanism, and also SN2 and E2. Now, the SN2 mechanism, as we indicated, that follows without formation of the cation, it gets helped by the nucleophile in order to carry out the reaction. So we'll get to that in a few minutes, but let's first talk about the carbocation. The carbocations can be rearranged. How? Whenever there is a driving force making another carbocation that is more stable. So one carbocation is formed, and if another carbocation from that can be made that is more stable, that will be the driving force to generate a second carbocation. And let me start with an example where we are doing an elimination reaction, and you have so you're starting with an alcohol, which is a secondary alcohol, and let's say you treat it with a strong acid. And the strong acid could be sulfuric acid, it could be phosphoric acid. So either H2SO4 or H3PO4 and heat. All right. And the expected product from that, because none of these can generate a very strong nucleophile. Okay, HCl would generate a reasonably good nucleophile as Cl minus or HI, but sulfuric acid and phosphoric acid don't generate a strong nucleophile. So in that case, it is undergoing a protonation. So you expect that protonation to happen, and it would form, because only one carbon has hydrogen. Even if you follow the same rule, it's supposed to generate this product. A double bond here. So let's write that down. So be a hydrogen as well. So okay. So this is what you expect to see. But it turns out that when this experiment is done, you will only get 3 to 5% of this product. So what happened to the rest? Okay. It turns out that we get two different products in which we get one which is this, and another one in which we have now, how did those two products come? Okay. In order to understand that, again, we can follow the mechanism and see what actually is happening to this. So the first step, if we follow the mechanism, would be protonation of this one, which is sequence expected reaction. All right. Subsequent step would be elimination of this alcohol and generating that cation that you would expect it to form. All right. This part, it's okay. And this is the one that would normally generate this product, as we expected. However, as you can see, that we can also characterize this carbocation as a secondary cation, right? It is connected to only 2 carbons. So this is a secondary cation. Carbocation. And it has the ability to rearrange. If it stays in the solvent long enough, it can rearrange, and in which there is a methyl group migration. And by doing the methyl group migration, let's see what happens. What will happen is that we generate a tertiary cation. And because the tertiary is more stable than secondary, this is actually a preferred pathway. You generate a more stable cation. And obviously this one now can undergo elimination in which this hydrogen would be removed. That would be the main product from this. So this would be removed by the base. In this case, the base could be water, which would pick up this proton and migrates here, generating this double bond. The other one that can be formed is formed from one of the ends where one of the hydrogen from the methyl group can be eliminated. If that happens, then you get the other product. And obviously, this one gives you the more stable because this is actually tri-substituted. As opposed to the first 2, those are both monosubstituted. First one and the third one would be the monosubstituted across the double bond. And therefore, this is a more thermodynamically stable product, and this is the major product in this case. So again, the driving force for the rearrangement of carbocation is the better stability of the resultant carbocation that is being formed. Any question on that? Okay. There are some other cases also where we see, in this case what we showed is a methyl transfer. There will be also cases where you can see a hydrogen transfer or a hydride transfer. In case of hydride transfer, rather than a methyl group, it will be an H minus, which includes the electrons of the bond to be removed from there. And that can happen in a situation where you don't get, for example, a distinct carbocation formation. So if we get, let's say, in this case, again, we can follow the path of this through the protonation of the alcohol. And obviously, this is a primary. Therefore, breaking this bond is extremely high energy. Therefore, this does not happen without the help from something which then can carry it out. And so let's say if you have water in this case, water can carry out this. H2O acts as a base. And that, if I rewrite this CH2, actually no, I don't have to rewrite that. So water can pick up this hydrogen. This bond goes and kicks out the water molecule. So the transition state, therefore, and we can draw the transition state based on how the bonds are forming and breaking using dotted line. So we can actually write the transition state C H dot 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 H. This bond is breaking. A new bond is forming with water. And this bond, one bond is there, the other bond is forming CH2, and this bond is now breaking. So it's OH, H. So now part of the cation is now moving over to the oxygen here because it's becoming H3O plus. So this gets a delta plus. This one also gets a delta plus. Okay, and so this would be the transition state of this reaction, in which, as you can see, this bond is forming, this bond is breaking with the carbon hydrogen, this new bond is forming, making this a double bond, and then the bond between the carbon and oxygen here is breaking. This becomes a water molecule that's eliminated. So final product, therefore, would be CH3, CH, double bond, CH2, and H2O plus, H3O plus. So this one is this one after the removal of the bond completely, you see a water molecule, and this is the final product. So what is this reaction now? This would be essentially E2 mechanism. So this is an example of E2. And why, again, E1 and E2, SN1 and SN2 depends on the kinetics of the reaction. When we are doing an SN1 or E1 reaction, the only substrate is the involved species. In this case, the water molecule, which is acting as a base, is also important. Therefore, if I have to write the rate expression of this, the rate would be K times the alcohol, which is in this case CH2OH, concentration of that, plus, in this case, the water acting as a base, which is also important. That's an example of an E2. It's first order in the alcohol and first order in the base, which is water. So this is an example of E2 mechanism, and as we compare with the SN1 and E1, this involves two species as opposed to one. All right. Now there are other examples of E2 mechanism, E1 mechanism as well. And one of the common one, more common than the alcohol reaction, is dehydrohalogenation. Which of course means you take out a hydrogen and a halogen from a halide. So if we have let's say we have a halide, and in this case I have written a secondary halide. Okay, this is a secondary carbon. But it can also be primary or tertiary depending on the situation. And now what we need to do is use a strong base. Now typically the strong bases that we talk about in the organic reactions are alkoxides. So these are normally sodium or potassium alkoxide. So let me just introduce you to the bases of this type. Sodium or potassium alkoxide. Now, what are alkoxide? Typically, an alcohol, when it's treated with one of the alkali metals, like sodium or potassium in general, they would essentially form a sodium alkoxide. So, in other words, what we normally do is like, let's take methanol. Okay. You take CH3, CH2OH, and drop some sodium metal directly onto that. And immediately you are going to see a very rapid bubbling of hydrogen that is escaping. Okay. What is happening is the sodium is reacting with the alcohol moiety and giving out H2, which bubbles out, and it's forming a sodium salt, NaOCH2, CH3. You can also write it the other way around, which is CH3CH2O, Na. And this reaction can be done with almost all alcohols. It is going to react fairly rapidly and we generate sodium methoxide, which is treated with methanol. Sodium tertiary butoxide with tertiary butanol. Which is considered a very bulky base and a very strong base as well. You can also do it not necessarily with alcohol. You can also do it. This reaction is too violent with water. In fact, it generates sodium hydroxide. But it also, as soon as you add sodium to water, it's going to catch fire. It's so violent. Okay. Potassium also. It reacts very rapidly and catches fire. But eventually that is going to give you the sodium hydroxide or potassium hydroxide as well. Okay. Now, you can do also this reaction with ammonia, which is a much slower reaction. So you have to actually let it start for a while before you generate that. But again, the same procedure, it generates hydrogen and NaNH2. So these are all examples of strong bases, and we use them for abstracting hydrogens from typically. They can sometimes act as a nucleophile as well, and we'll deal with that in chapter 8, going through more detail with that. But I wanted to give you the brief description of how some of the organic strong bases are generated. All right. So let's say if you use a strong base, any one of these would work. Yeah. Then the objective of the base is to pull out the hydrogen. And it does that in one step, as we have shown in the other case. The base pulls out a proton, and again, it has an option of, this is the alpha position, there are two beta positions. And it's going to do it from both, but it again follows the Zaitsev rule, in which it produces a double bond here more commonly, which is more substituted than the other one. So this is a major product, and this is a minor product. So the base is essentially pulling out a proton from either one of the beta position, and at the same time the chlorine is actually taken out. So the mechanism is very similar in the sense that it's going to, let me show you here, if you have a hydrogen, and let's say the base is represented as the attacks here, comes here, kicks out the chlorine, which is the living group in this case. And again, we can write the transition state structure the same way we have done the previous one. So again, dot, 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 which is the bond is partially broken with hydrogen. Okay. It attaches with the base. This is also partially formed. And the chlorine bond is partially broken. And a new bond is formed partially here, which ultimately gives rise to this product. This is the DS. So again, you can see that the pattern is very similar, and you are able to predict the product based on that. So the dehydrohalogenation is essentially, in general, this type of reaction where you do the elimination of the hydrogen, or in this case hydride, and the halogen at the same time. reactions again follow the same pattern as we have seen before. Typically, in halogens, I minus works better than Br minus, which in turn is better than Cl, and chlorine is particularly used. So these three are normally used for dehydrogenation. So the reaction rate are dependent on the halogen as well, because these act as a living group. Yes.
Situation is the same as we've seen before, that the higher polarizability and the more spread out you're going to get charges.
Right, because the species that is eliminated is either I minus, Br minus, or Cl minus. And if you compare the surface area, I is larger, so you can accommodate the negative charge better than Cl minus. And again, fluorine is very small, so it's got that polarizing factor. Again, it's in the least of the halogens. All right. So we broadly went over the E1 and E2 mechanism, just like we also did with the SN1 and SN2 mechanism. And now let's try to do a problem and see how we can relate all that. And this is actually one from your text, and it will give you a pretty good idea of the important aspect of it. This is 5.45. And I don't know if you have already done this problem, but you can at least think about it rationally. What they're asking is that you have the following molecules available. Okay, so the objective of this problem really, it's asking you that we need to prepare this compound, right? And you are given two starting material, either A or B. You can select your starting material, and then tell me how you are going to carry out the reaction, and what would be the better way to make this. Now think about it for just 2 minutes. It's a rational explanation based on what we already discussed, and you should be able to answer that question. Which one would you rather pick? Let me take a poll. How many will pick A? Only 3 people. How many will pick B? There's a more response of B. Yes, that would be B is the more logical to be picked. And let me explain why. Because if you are to do this reaction with A, what we need to do is use a strong acid, okay, so that we protonate the alcohol, generate a carbocation, and then make this product through elimination, right? So it's an E1 process. Okay, use, let's say, phosphoric acid, H3PO4, or sulfuric acid, and heat. And the practical problem of this approach is that you are making a carbocation. This would be the first product that is generated. And and your expectation is this will generate this. But as I mentioned, because of carbon para and rearrangement, a significant product would be essentially a rearranged product where we'll get this, which will end up giving you a major product as this. So only a small amount of the product that we intend to make will be formed. Okay. So this is not a desirable method to make that, because you end up getting something else as the major product. And on the other hand, if you make it from B, this carbon has no hydrogen. Essentially, all of the hydrogen that will be taken out through E2 mechanism. This one is following E1, and this is going to follow E2, where one of the hydrogen from this can be taken out by using a strong base, such as sodium ethoxide. And so, the way this reaction would go is pick up this proton and kicks out this, generating C as the major product and the alcohol. Okay, so this is going to generate mostly like 80 or 90% of this product. On the other hand, this other case, it would be less than 10% of this product, and most of the other product would be side product. Okay, so therefore, this is really an application of what you learned on E1 and E2 mechanism. That's what you need to apply. If you carry out another E2 reaction, and typically again, the other thing I wanted to emphasize is that, let's say you are using potassium tertiary butoxide, as in this case. You want to use the same alcohol, tertiary butanol, because that is one of the products that is being generated, and you use that as the solvent. If you use sodium ethoxide or potassium ethoxide, then you want to use ethanol as the solvent. If you use methoxide, then you want to use methanol as the solvent. Okay. Anyway, in this reaction again, the E2 mechanism that we are looking at would be forming a double bond from either one of these two beta carbons. This is alpha, this one beta, and this one is beta. Okay. And the only fundamental difference between them is their thermodynamic stability. So let's write both products and see which one would be major in this case. This is one product, and this is the other product. And the basic difference between these two compounds is that this one has a E double bond, and this one has a Z double bond. And in 10-member ring system, as in this case, okay, the Z double bonds are more stable. Okay. So this is more thermodynamically stable product because you introduce the double bond in the Z direction as opposed to E. And as a result, this is really 85% product generated here, and this is only 15% because it's less stable. So it does follow the thermodynamic parameters of the product that is being formed as well in E2 mechanism. All right, so let's just go back, kind of try to review what we learned based on the potential energy diagram. So let's say okay, so the very first step is protonation, as you have seen if you start with alcohol. Okay, and so this is going to generate positively charged oxygen, which is connected to two other hydrogens. The next step is the rate determining step, where we get the breaking of this bond. Therefore, the transition state would look like this. R dot 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 O H H. You still have delta plus R. Finally, when this bond is broken, then it's going to generate R plus H2O and whatever else is there. So this is the formation of the carbocation. This part is same for SN1 and E1 mechanism. Right? The next step is relatively small energy demand to generate the product from that, and this is a SN1 pathway where we get our whatever the halogen. Let's say if you use HCl or HBr. This would be that one. Let's say X is the halogen that is being produced here. And again, you can draw the transition state, the third transition state in this case. This is TS2, and this would be TS3. You can draw based on the bonds that are forming and breaking. In this case, the bonds are forming only with R plus. So you write dot 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 X. All right, SN1 path. The fundamental difference is that in the absence of a good nucleophile, such as X minus, what it would have, which is slightly higher energy, it can undergo elimination to an alkene. Okay. Depending on the R. And in this case, I'm assuming that the R is secondary or tertiary. R is secondary or tertiary. But as soon as you switch that from secondary to tertiary to primary or alkyl group, then the energy of forming this gets so high up here that it cannot really do that effectively. Which essentially what it does is that rather than breaking this bond, it needs an attack by another species, which could be the base or the nucleophile. B is the base, or Nu would be the nucleophile. Either one of them can attack and essentially carry out the rest of the reaction, And even though that is higher than this, it is still can go in one state to the product of either alkene or to the product here. So that is really the fundamental difference between the two types of reaction, SN1, E1 versus SN2 and E2 reaction. And you can combine all of them. You need to remember what is very important is the